Okay, the question that I'm going to discuss now is to explain this statement here, the statements here, which says that there are two sources of quantum corrections. One is the optional paths in configuration space, and the other is local modification of the measure. So before I go on to explain these statements here, let me first remind you about the context where the discussion is coming. It's in lecture 2, part 2. So what we were doing is that first we got the path integral statement due to Feynman, which is that the matrix element, the relevant matrix element, is given by path integral of the phase, the Dirac phase here. And then we were asking the question that how to show the equivalence of that result with the usual Hamiltonian quantum mechanics. And the result that we had shown here is that if you take the usual system, like where the Hamiltonian is quadratic in momentum, Hamiltonian is a phase space quantity and it has momentum dependence. So if it is quadratic in momentum, simple enough, more conventional or standard system, then it is exactly same. The matrix element obtained from the Hamiltonian time evolution is exactly same as the Feynman path integral, where it is given by this. Now, when we say that, so that means this Feynman path integral matches with the Hamiltonian result. And when we do when we take a more general Hamiltonian, which may have more complicated dependence on P, then the result is not so simple, and it is given by this. So you see that this is not only that phase e to the power I by h bar s, but it multiplies with a factor m, which is an h bar expansion like this. This is the result. And therefore, as if we do not have as if the path integral statement is not valid anymore. But that point of view is not right. So that's what I'm going to basically explain now. First of all, when we say that the path integral statement is right, is equivalent to the Hamiltonian quantum mechanics, we are taking we are saying that there is a path integral. The result is given by path integral of some quantity, the integrand, and that integrand is basically a phase which is given by the action. But this action is obtained from the Hamiltonian by a Legendre transformation. We get the Lagrangian through the Legendre transformation, and that gives you the action. So let me call it a classical action. And this process of Legendre transformation can be viewed in two ways. One is that you are going from Hamiltonian to Lagrangian description. Also, another way of looking at it as that you are going from the phase space to configuration space. Okay, in the phase space we have two variables x and t. In the configuration space we have only one variable, and the classical paths are given by second order differential equation in x in the configuration space language. And here we have first order differential equation both in x and t, but the number of equations is more, which is equivalent to that second order expression, second order equation. Now, these are called the Euler-Lagrange equation on this hand, and in this hand, these are called the Hamilton's equation. And the two parts of the Hamilton's equation. The first one it relates. So you give x dot as del h del x del p, that relates p as a function of x dot. Okay, so this relates momentum and x dot and the velocity. Okay, which is used in the second stage where we have an expression, a first order differential equation in terms of x. When you do that, you get this Euler-Lagrange equation, which is second order in time derivative. So this is the background. So that structure is an entirely classical structure, and that classical structure has been adapted in order to refer to what appears in that integrand, when we say that the phase is given by path integral phase is given by the action, this action actually has this whole background information. This is how it is constructed, and this construction is entirely a topic of classical mechanics. Okay, so I just wanted to remind it. We take it for granted, but here it is important to note that, because this is going to be relevant now. Now, what we did is in the when the Hamiltonian has more general dependence, of course, in a arbitrary dependence of momentum, there is no way to do an integration. If you don't know the function, you cannot do the integration. So momentum part of the integral, the phase space path integral, cannot be performed unless we resort to certain type of approximation. And here the approximation is a small h bar approximation, as this calculation shows, where so we have two types of paths to integrate over. In our actual configuration space language, we had a space. I drew some cartoon, the function space, where the each function is represented by a point here. Okay, that is the space of functions. A space of functions means space of configurations. Now we are not only have configurations, but we have phase space. So not only x, we also have a p. So we have phase space configurations. So in this case, we will have this type of independent paths, two independent function space. One is the function space for x, another is the function space for p. So both of them are infinite dimensional, both of them are path space, space of paths. So here a particular point represents a function like this. Here a particular point represents a function like that. And an arbitrary point in this space is a combination of these two paths. Okay, now this is the space over which we are doing path integral now, when we have a path integral in the phase space path integral. Okay, so now we want to get rid of this momentum space part altogether by performing the momentum space integral. That we cannot, I just mentioned, we cannot do, and therefore you have to take some approximation. What kind of approximation should we take? Now, this calculation shows a particular way of dealing with this situation. Now, what is that way? The way is that we know classically, the classical process that I just described, showing you the previous slide, there is a Legendre transformation which relates P and X dot, and helps you to go from Hamiltonian to Lagrangian. P and X dot. So what is that relation? That relation, how does it impact in this picture? What is the impact of that Legendre transformation in this picture? You see, these two functions, both x and p, are independent. Okay, that is how the path integral has to go. Now we take, if you relate p to x dot, then that basically gives a restriction between p paths and x paths, because once you know an x path, given any x path, you can calculate the x dot, corresponding x dot, and if you relate that with p, then that basically is a restriction between p and x paths. So for every x path, there is a corresponding p path. So if you take any point here that corresponds to an x path, then it automatically determines a point here, because that is how these two paths are related, which means there is a subspace. In this space, there is a subspace. How, if you have a function x and y, if you give a point x, then that fixes a value for y, which means there is a subspace in this two-dimensional space, which is one-dimensional subspace which relates x and y, right? This curve relates x and y. Given any value of x, you get a value of y through this curve. Similarly, here also there is a subspace of points on which which basically relates every x path to a corresponding. So if you take an x path, you took a vertical line, go to this path, this surface, and then a projection to P, that will give you the P path. Okay. So there is this is a surface which relates. So it essentially brings down to if you use this surface to eliminate P, because now P is related to X, then the P is eliminated from your calculation, and your entire calculation can be done from the point of view of X space. That is the idea. Okay, the calculation is brought down to configuration space again from the phase space. So just remember this picture. I'll have to lift my pen and explain something else, but I'll come back to this picture again. So that is the idea. But the point is that this is the Legendre transformation surface. Okay, this is the classical Legendre transformation surface. But your actual integral, path integral, is everywhere. How are we going to use this surface? So what we do is that we define on this surface, the momentum configurations on this surface, let us call P0. P0 are those momentum configurations which satisfy this constraint, which are lying on this surface, which are related to X in a particular way, X paths in a particular way. Okay. Now, all the other, but in our integrand, in the path integral, has momentum P, not P0. So P minus P0 is the variable which has to be integrated. So we consider, we take a limit, we take a situation where the maximum contributions is coming from this surface, which is basically the classical Legendre transformation. But since the entire momentum space path integral involves all the P's, this is like choice of an origin. Okay, this is a choice of an origin, but now it is not only a choice of an origin. I can do an integral P minus P naught, where P naught is fixed. Then I can do integral that is equivalent to doing a P integral. I can do the integral in powers. I mean, if you define Q to be this and do an integral over Q, then that is equivalent to doing P integral, right? But the point is that that is not only what we are doing. We are defining Q in such a way that this P minus P naught is not only Q but root H bar. So P minus P naught is not only Q but root H bar times Q. When what it means is that, so let me not draw two-dimensional surface, but to simplify it, let me draw one-dimensional lines. So this is your configuration space, sorry. So this is your configuration space function space, and this is momentum function space. And then this is the Legendre transformation surface. So this is what this is, the value of this is P0. Okay, the P this is a P0, this is the surface of P0. Okay, which has a particular relation with X dot. Now what we are doing is that we are defining P minus P0 divided by root H bar, P minus P0 divided by root H bar to be Q, which means that in the H bar going to 0 limit, you have to be, for order 1 Q, if H bar is very small, in order to get an order 1 Q, your P minus P0 will have to be that small. If P minus P0 is finite, but you still take root H bar, still take H bar to be small, then this will be very large. So a finite distance from P, this surface, is pushed away, very far away, okay, by scaling it with root H bar and taking H bar going to 0 limit. Now, since you are taking H bar going to 0 limit, only those values of Q's are order 1, where when P is very close to P naught. So it is, so that means all the contributions that are the contributions that you are receiving from P integral are close to P naught. So that is the formulation of semi-classical expansion, because what you are designing the computation in such a way, as I have explained elsewhere, that h bar cannot be set to 0, or you cannot take the limit h bar going to 0, because h bar is a fixed number in nature. It is you are actually changing the system. When you are taking h bar to 0, you are taking the system, the typical momentum of the system is such that p minus p naught by root h bar is very small. In that case, the maximum contribution will come from near the surface. So at the surface, you are getting most of the configuration, and then the subleading configurations are coming from configurations where p is near p naught, which is not satisfying the Legendre transformation equation, but some other values of p which they are near the surface, and those contributions are appearing as higher order in h bar corrections. These contributions are calculated here in power, when you expand in powers of p minus p naught, and do that because you are expanding in powers of p minus p naught by Taylor expansion around the surface. You can do each term, for each term you can do the momentum integral, because it's just a power p minus p naught to the power n, and you can do the momentum integral and get the result. This is what the advantage of it. So if h bar is very small, then each higher order terms, which are higher order in h bar, will be more and more suppressed, and therefore this expansion makes sense. So if your system is such that it fits into this formal discussion of h bar going to 0 limit, then this result is meaningful for that system. Otherwise, it is not. If it is a fully quantum system, there is no classical limit. The system size is comparable to h bar. Then you cannot perform such expansion, and you cannot get that result. You have to do the momentum integral explicitly for all values of momentum everywhere in the momentum space. All of them are equally important. It is not that some specific near some specific surface the contributions are more important, and as you go away from the surface, the contributions are dropping. It is not that situation. It depends on the system. If the system is such it fits this criteria, then only this calculation is meaningful. That is, this calculation shows, and that is what the actual meaning of h bar going to 0 limit, physical interpretation of that. I have explained that in more detail in another video where I'm discussing stationary phase argument. Okay, so that is the idea. So that means these quantum corrections, which are coming from momentum configurations near the Legendre transformation surface, they are giving further corrections. So these are like quantum corrections to the Legendre transformation itself. If you collect all these, corrections and the result that you get here, and now write m to be equal to e to the power I h bar Sm, where Sm is, this is how m is given by this defines of what Sm is. Then the entire result is the configuration space path integral e to the power I by h bar S plus Sm, where this Sm is a quantum. This Sm m has h bar dependence, so Sm will also have h bar dependence, though S does not have. S does not have h bar dependence because this is constructed classically from the Hamiltonian through the classical Legendre transformation. But then you can look at the entire result to be a configuration space path integral with an action which includes quantum corrections, effects of quantum corrections around the Legendre transformation. So the Legendre transformation itself receives quantum correction in that sense. So in that sense, if you are allowing your action to be defined in such a way that that includes quantum corrections of the Legendre transformation, then the same path integral statement is valid, because this S has the quantum corrections of the Legendre transformation. Okay, so it is a when you say when you refer to action through only is classical procedure, it's a standard way of referring it. But there is no logic, in a quantum theory, in the Hamiltonian formulation, whatever result you get, why would you get the same? Why would you get a result if you have to write the same quantity in terms of path integral? Why would the classical action play the role there? It is the entire quantum action, no, that would play the role in calculating the matrix element, right? Classical action is relevant for classical mechanics. Classical action is relevant here also only in small h bar limit, because the quantum action is predominantly classical, and then on top of that we have some quantum correction. It is in that sense. But if the system is fully quantum, then there is no way to do it. Okay. Now, this is one way of looking at it, that the Hamiltonian formulation of quantum mechanics is equivalent to a path integral formulation if you know how to construct that action. The other way of looking at it in the following way: if you are standardizing the construction of action through the classical process, that means this action, whenever you talk about action, you always refer to the classical action. That's a convenient, or that's an effective way of discussing these things, because the full quantum action a priori you don't know how to construct. You don't have the result. It's a result of the path integral that will tell you for a particular system what the quantum action is. Now, if you want to refer to a very concrete action, then you would take the classical action. It has a very concrete construction, concrete result, right? For a given Hamiltonian. If that is the case, then your result is this. Okay, then you should view the result in this way. Instead of writing m exponentiate m in terms of Sm, you should write m as a separate factor sitting there and call it a modification of the path integral statement, which is okay. It's just a nomenclature. Now, in that case, it is in that sense these statements were made. Let us now look at this. What is the meaning of this statement? The meaning of the statement is that, first of all, this entire analysis calculation is valid in the small h bar only. So this path integral that has not been performed because action is arbitrary, this path integral is also has to be done, and it will be calculated only in small h bar, because that is what we have assumed already. H bar is small. So in this picture that I drew here, this is your P0. Okay. Now you have brought down the entire calculation on this surface. So then you are calculating a path integral in X. Now, what I wanted to say, I will come back to this picture again to explain the measure, but let me first explain what this first statement is. So here in this fx, if I just go back to the previous cartoon of fx, this is a path integral in this fx, and it has to be done everywhere. But since h bar is small, there are certain maybe isolated extrema of the action. Okay, this is where the action extremizes. This action extremizes. If there are certain isolated extrema of the action, classical action, then these are classical solution of the theory. And since h bar goes to 0 because of the stationary phase argument, this path integral also will have maximum contribution from these isolated extrema, and then there will be h bar corrections. The points near these extrema will also contribute, but their contribution will be small, because the contribution will die down around these points, and those contributions will be small and can be quantified in powers of h bar. So this path integral also, this configuration space path integral, will also be leading to another set of h bar expansion like this. Okay, and there the leading contribution will be from the isolated extrema. So this is the meaning of this thing. So the entire set of quantum corrections are given by the all these h bar expansion. One h bar expansion is sitting in M. Another h bar expansion is supposed to come when you do this path integral, x path integral, because that will also pick some configurations, classical configurations at the leading order, and then a higher order h bar correction as subleading order. So there are two sources of such corrections, h bar corrections. So the second one is due to the optional paths in the configuration space, as I drew here. These are isolated points, and then the points which are surrounding the neighborhood, they are optional paths. They will also contribute, and those are the quantum corrections. So this is one set of quantum corrections, and the other set of quantum corrections is in M. And let's see what is this M. So if you set h bar to 0, or M is M first leading term is M0. If that is not 1, then it is just an overall factor. You can take M0 outside, and then the series starts 1 plus h bar M1 by M0 and so on. So the overall factor is not important. Our discussions are all up to the overall factor. So if M, so let me take this to be 1, then the leading term to be 1. So if you take h bar going to 0 limit, then leading term will be 1, which is the case here. Okay. Now here, because of this quantum correction to Legendre transformations, you have additional factors, and this can be viewed as measure, local modification of the measure. First of all, what is local modification? So if you look at this calculation here, p minus p, so there are two things here, this p integral, this t integral, and then p minus p naught has been written in terms of q, and therefore we have q integral and t integral. So this is x integral. Within the x integral, this entire expression sits, and if you take any typical term that has a q integral, but also this bracket which is a t integration. So k's are given, k's are functions of x dot and t. X is a path, so that is within the t integral. So that means to calculate that quantity after performing the q integration, q path integral, the quantity that you are left with will involve an integral of path. So then it is like this thing, because S is also an integral of a path. That is why it's a path integration. If it is only x, then you are integrating over x. It is not integration of x, it is integration of x path. So it has to depend on the path. Should not depend on a particular value of x. So the point that I'm trying to make here is that these are path dependent quantity. After doing the q integral, you get a x path dependent quantity because it has integral over t. Okay, knowing only x does not help. You have to know x of t from ti to tf. The entire function has to be known. Then only you can get this result after the q integration is performed. So these are the contributions m1, m2, and so on, right? These are path integrals. So basically, I should use a notation here also, a path like this. It is not a local function of x, but it is a local function of the paths. So that's why it's a local modification of the measure of the path integral. Measure of the path integral means, so let me explain what the measure is. When you calculate an integral, say f versus x, and then you take x between the slice between x and x plus dx, and over this small dx you have fx to be constant, not changing over this. So the area which is contributing to the integration is fx dx. This is what you get, right? If you go to higher dimension, then say x and y, and you have fxy. So here also you have an area element which is given by dx dy, and then the height f x comma y. Okay, and then f x comma y dx dy is the volume of this entire thing. Okay, and that is contributing to the integral. Now, this is not always the case, because we are assuming that we are integrating f on a space. There are two portions here. One is the integrand, and the other is the element, area element, or the volume element, which is coming from the space over which the integration is being performed. What is that space? In these two examples, the space is a flat sheet or a flat line, where the coordinate element dx gives a length element dx. If you have a code in 2 dimension, a coordinate element dx dy gives an area element dx dy. However, because that is a flat surface in a Cartesian coordinate system. But if you take a surface of a sphere, so if a surface of a sphere then probably you have two angles, say theta and phi, then d theta and d phi would be the coordinate element, but that is not the area element. The area element involves r. When you write things in terms of r theta phi coordinate, you know that it has a non-trivial component contribution depending on the value of r. So you can understand it easily. When r increases, the sphere increases, the area increases also. So it is r dependent. Okay. So that extra factor is an m. So there is an m times d theta d phi. So that extra factor tells you that the area, the coordinate element is not same as the area element. It is because the space is not flat, it is curved. It is because of that there is an extra factor like that. Okay, and then if you have a function there, then you have to multiply f with that. So f m then coordinate element. This coordinate element is always there, but question is that whether m is there or not. If you know the space, then you know what m is. But if you do not know the space a priori, then you don't know, then you have to have some guidance to find that measure. This is called the measure factor. Okay, so what we see here, this is exactly how m appears in this integral. So as if this m is giving a measure factor to the path integral, to the space that I have drawn here. I have the cartoon. I have explained earlier, the point, every point corresponds to certain path. Every single point corresponds to certain path. Now, I had also mentioned earlier that if you take a Fourier transform of this function x of t, then the Fourier coefficients can be viewed as infinite dimensional coordinate system in this space. But that is only a coordinate system. That does not tell you, if you had to integrate in this space, what would be the measure. That is not a priori clear. Okay, so if you had considered in the first case, if this measure, this like the flat measure, the flat space where you have dx dy as the area element, if this is the case for a simple Hamiltonian, where action, the entire action that is sitting here, for the path integral, is exactly the classical action. That means it follows the Legendre transformation classical rule. Then this measure is deformed, has an h-bar deformation, which means that the space f, curly f, is not any more like a flat space for which we got measure dx dy. It has become more like a sphere. Okay, that means the space has changed, and that is a quantum deformation of the function space. And this quantum deformation is coming because of the quantum corrections to the Legendre transformation itself that we described. Because Okay, so that is one way of looking at it. If you look at it as a measure, then basically the quantum corrections. There are two sorts of quantum corrections being in a semi-classical expansion. One I explained earlier, and the other one is deforming the measure or deforming the space itself, the function space itself. So that is the meaning of this statement. If it's only when you look at it this way, and the other way of saying it is that, which is not very useful but completely rational, is exponentiate m and consider the total compact quantum action. So in that sense, there is no question of, you cannot ask this question whether for this Hamiltonian path integral is a valid statement or not, because path integral is a valid statement. You can always write in the path integral form with a certain action. If you can do the momentum integration, assuming that, then you can certainly write a path integral with certain action, which is a quantum action. That does not have to be. So that means you either define the system by a Hamiltonian and do Hamiltonian quantum mechanics, or define the system by an action and do path integral quantum mechanics. It depends on the system. If the system is simple enough, if the system allows you to do momentum integration, then you can relate these two. But a priori, there is a relation, but it may not be easy. That is the message.